I'm providing some extra help for question 3 here on assignment 0, where we have two different options in our game. Play our arcane spell card right now, or pass, let our opponent draw, and risk them winning to potentially improve our odds of winning the following turn. And we're asked to determine which of these two options is the best in terms of giving us a better probability of winning. If we go with the first option here, then we have to follow these rules. We fire 10 random arrows or bolts at the enemy ships. And there's 3 enemy ships. A hero ship with 5 health, 2 grunt ships that have 2 health each, and a destroyer ship with 10 health, or HP for short. Every arrow will be fired one at a time and will target one of these enemies as long as the enemies have more than 0 health. If their health at any point is 0 or less, then they are no longer selectable as a target. You could think of that as like battleship. You destroyed a battleship target, you can't attack it again. It's already destroyed. Every time an arrow hits a target, it'll lower its health by 1. So if, for example, the hero ship had 5 health, and I hit it with an arrow, then it goes down by 1 health to 4. And I hit it with another arrow, it'll go down by 1 health to 3, and so on, for however many arrows hit that ship. And again, the third point, if any of the enemy's health drops to 0, if any of the ship's health drop to 0 at any point, they are no longer selectable as a target. The winning condition is that this hero ship goes to 0 HP. It's destroyed. If you do not destroy it, you lose. So, which of these two options is better? And I want to begin here with a simpler variation of the problem. So let me write the simpler variation right here. Simple variation. Presume that each target has 100 HP. So each 4 of these targets have 100 health. Further, presume we still fire 10 arrows at random and abide by the same logic in the original problem. Meaning they still will hit one of the targets for sure. There's no probability of them missing. And they will still do 1 damage for whatever target they hit. Then, the question is this. What is the probability that we hit one specific target, the hero, 5 times in 10 arrow shots? What is that probability? Because that would help us, if we can understand how to answer that, that can help us understand how this question should be answered. And the good thing about this is this problem can be solved via the binomial distribution. And why do I say that? Why the binomial distribution? The reason for that is this. The binomial deals with some fixed number of independent trials where each trial has 2 potential outcomes that we call a success or a fail. So the key parts of the definition: independent trials, fixed number, success, fail for each. Independent meaning the result of one trial doesn't influence the other. Fixed number meaning there's a specific number of trials, in this case the number of arrow shots. Success for fail is a condition that we associate with each trial. So each of the bolts is a trial. Each bolt or arrow, and the way that I've called it in the question here, is a trial. We have 10 trials, 10 arrow shots. We can define from this success. Success is it hits the hero. Failure in any given trial is it hits any other target. Right? And because I said all 4 of them have 100 health, there is no possibility that any one of them will be destroyed. Meaning that in all arrow shots, they're equally likely to hit any one of the 4 targets. What that means is the probability of this event is 1/4. The probability of the success event is 1/4. I have 4 ships. They're equally likely to be hit by an arrow, so each one has an odds or probability of 1/4 or 0.25. So then the number of trials, which I'll call n, is 10. The number of successes we're looking for, which I call k, is 5. And the probability of a success, which is p, is 0.25. And these are important because we could put them in R in a function called d binom. This accesses the probability mass function of the binomial and tells us the probability of getting some certain number of successes, in this case 5 hits, in a given number of trials, 10, with some given probability of success on each trial. So if I run d binom 5, 10, 0.25, 5 is the number of successes, 10 is the number of trials, 0.25 is the probability of success on each trial, I get 0.05838, 583,992. So let me very quickly copy that over. And then let's discuss the interpretation of that. So this is the answer from R. And how can we interpret that? Is we can interpret that as saying in this simple variation, that is the probability that we would expect to occur for this type of event. But there are some important takeaways here. In the actual case, the original problem, we know this. Every target has different health. Some targets are more likely to be destroyed. So that is, for example, these 2 ships with 2 HP each are more likely to be destroyed than the hero or the destroyer. Logically, it's more likely I'll destroy something with 2 health than 5 or 10. And that also implies that this, if 2 is correct, then targeting the hero ship becomes more likely. Intuitively, that makes sense. If I had 4 targets and one of them was destroyed, now I have 3. The probability of me hitting one of those 3 is no longer 0.25. It's 0.33, 1/3. And so that's a higher probability. It becomes more likely. The implication of that is that we should expect our answer to be larger than this, because this is the probability that we're equally likely to hit any one of them. But that's not the case in actuality, right? That also leads to my final point here, which is this. We cannot use the binomial for the original question. Why not? Why can't we use it? Well, think about what the binomial assumes. It assumes these 2 things. It assumes independence and a consistent probability of success. Neither of these are true in our original problem. If, for example, I fired 4 arrows, and let's say that 2 of the arrows hit this one and 1 hit this one so far. So I fired 3 arrows, 2 of them hit this one, 1 hits this one. One of these is now destroyed because I had 2 health. When I go to fire my 4th arrow, where it lands depends on where the 3rd one hit or where previous arrows hit, because it got rid of a target. What that means is that each trial's outcome is not independent of the other ones. So it violates the independence assumption. Further, the probability of a success is no longer 0.25 all the time. If the number of targets were to drop, in this case that I've illustrated, the probability of success that we defined as attacking or destroying this ship increases. So therefore, this is violated. And if these 2 are violated, the binomial cannot be applied to the situation. And the fact that the binomial can't be applied is the reason why we're using Monte Carlo in the first place, is because we don't have a better model to estimate this. So that's the motivation for it. Now let's go into some intuition, some help here. The first thing is, how can we determine if a target has been eliminated? So in another way I can put that is this. How do I find out which ship goes to 0 HP in the simulation? What is the right way of doing that? And you could think about probably a million ways of doing this, and I want to show you the first way and then another way that might be a little bit easier. The first way is this. We can do a loop. So we'll set up a loop over the existing healths of the enemies, and then we'll check for a condition. And in order to do this, what we want to do is we want to loop over the indexes of the healths, because we want to get the position back of which ship has the 0 health. I'll put it this way, I'll make it easier. So health vector. Let's say we have 5, 2, 0, 10. Let's say the third ship now is at 0 health, and the other ones were not hit. Let's say 2 arrows hit this one. So if we run that, we get this vector here. Then we do a for loop, and we can have this, instead of being I, we can have it be HP in. And now if I just do health vector, I just want to show you what happens if I do this. If I just do this, have a look at what the output is. 5, 2, 0, and 10. So I get the actual literal values from the vector, but that's not the indexes, right? This is not position 5. This is the value 5, but I want the position. So in order to do that, I do this. I do sequence along and wrap it around this. And that will give me the actual index if I run it again. Let me pause, just check the syntax real quick. Yep, I accidentally added a dot. It was an underscore, but sequence along. And what this will do is, sequence along, what it will do is it'll generate indexes that correspond to each element of the vector. So index 1, index 2, index 3, index 4, and here we got our indices as outputs. And then with indices, what we can do, and let me just make this more clear, is that's an index, IDX for short, is I can say this. So continuing, what we can do now is we can set up a conditional logic, right? So what we can set is this. We can say if in the original vector at that particular index, because this is an index, this is a position into a vector. It'll be a number like 1, 2, or 3, up to 4, because there's 4 elements. If in that vector at that position equals 0, then we know we found a 0 health one. So we can do like a cat here and say the ship at position HP IDX has 0 HP, and then backslash end. And if we have a look at this, the ship at position 3 has 0 HP. And so now we could even do, we can even assign this to a variable and then use it somewhere else. And I want to show that very quickly. Let me pause. You could potentially do something like this, where you assign this to a variable, and then you can use it later on to index and get the output that you want, or use it to check a condition, or remove ships that meet this condition, and so on. That's one way. I think there's an easier way, and that's using a function called which. So which. The which function will give us true indices of some logical object. In a simpler term, it'll take a condition, apply it to a vector of the same length that we specify to get a logical vector for it, and then find the indices of all the true values, so values in the vector that meet our condition. So again, just to show you visually, because I think it's easier to explain. Health vector C 5, 2, 0, 10. all over again, run it again. And then now we do this. Which HP equals 0? Double equals because we're doing a logical comparison. Run that. And we get the output. We should get the output of the indexes here. Let me pause quickly just to double check why that's not working. I realized a simple mistake I made. You're supposed to pass in the actual vector. I just passed in something that doesn't exist, so I had no idea what to do with it. But when I pass in the vector with the condition, it outputs 3, which is this index with the 0. And just to show you, if I had more ships, like 2, 2, 2, 0 here, and I ran it again, I get both of these now, 3 and 8. This one here and this one here as outputs. And that's a one-line statement that gives you a position that I think is a lot more compact than this and a lot more efficient. And this is the approach I would recommend when you want to check that condition. Now let's move on to another thing, which is the scenario of passing. What is the probability of that? So if we flip back to Paint here, option 2 is that we pass, right? And so we want to know what is the likelihood that we win in option 2. So that's composed of 2 distinct probabilities that need to be combined. Let me explain. The first probability is that your opponent loses, right? Your opponent draws a card and that card does not win for them. The second probability is that you draw a winning card on your subsequent turn. And that's, we know that happens with a probability of 50% or 0.5. Either you have a 50% chance of you draw the winning card or you draw a losing card. The opponent loses event, well, we know that they win with 32.33%. So the complement would be losing. So that's 1 minus 0.32333. And, handy dandy R, 0.6767. So those are the 2 probabilities that we're dealing with here. And the overall combination here is that we multiply these probabilities to get gives us the overall probability of option 2. The overall probability of our opponent losing and of us drawing the winning card, because those 2 factor into this option. The final thing that I will mention for this question briefly, or actually not the final thing, but one of the final things, is you will need some sort of loop in order to approach this problem. And I would recommend keeping it as simple as possible. You don't have to overcomplicate it.